Good morning, students. How are you? I hope you are doing well and enjoying your daily classes. This is Anirudh Mehta, your chemistry mentor, back with another video of isomerism. In the last class, we have studied about structural isomerism of the type chain, position, and functional and ring chain. Chain, position, functional, ring chain. These four isomerism we have completed in the last class. Chain, position, functional, and ring chain, which is a part of functional isomerism only. Okay, so hello Thanu, good morning Chandana. These are the topics we dealt with in the last class. I have a little pain in my shoulder, so I won't be able to write it right on the top. So I'll be writing at the bottom part. But because today I've got a presentation, most of the things are written only. Because of my shoulder pain, I won't be able to write much. But wherever required, I'll be writing in the half part of the board. Okay, I can't lift my shoulder much above this height for today, or maybe for next 2-3 days. So please bear with it. Okay, all right, guys. So today, what should we do? Today, our topic is going to be what is metamerism? And second topic, we are going to start with geometrical isomerism. Okay, these are the two topics that we are going to do today. Tautomerism is a topic which will be more easy to understand after you have completed your, electronic effects like mesomeric effect, hyperconjugation, because many concepts in, tautomerism come from the topic hyperconjugation and resonance as well. So that will be done later. So we'll complete the structural isomerism by doing metamerism today. And after that, instead of doing the tautomerism, we'll be starting with the geometrical isomerism, which is cis trans, Ez, and syn-nt. I hope everybody is fine with it. Are you all ready with your pen and book? Shall we start? Are you all ready with your pen and notebook? Are the pen and notebook ready? Shall we start? Quickly tell me. Are the pens and notebooks ready? Shall we quickly start with metamerism today? So when we talk about metamers, yes. So metamerism is a type of isomerism which generally coincides with the positional isomerism and chain isomerism. Okay. So metamerism will always confuse you with chain and position. So what is metamerism? See carefully. Whenever you have a functional group which is a bidirectional functional group, means both side alkyl chains are attached. This side also alkyl gets attached. Let's say I'll write alkyl as R1, here alkyl as R2. So there are few functional groups which are called as bifunctional functional groups. Bifunctional means both sides they attach a alkyl chain. Like ketone ke this side also carbon is there, this side also carbon is there. Like ester, in ester this side also carbons are there, this side also carbons are there. Like ethers, these are called as bifunctional groups. So in a bifunctional group, whenever we change the nature of two alkyls, let's say initially there was a methyl and a propyl here. But in the other compound, functional group is same, but these two alkyls become different. Let's say this become R4, this become R3. They are going to be called as metamers. Okay, so what are metamers? What are metamers? Metamers are the isomers carrying bifunctional group with same molecular formula but different nature of alkyl chains on both sides. Different nature of alkyl chains on both sides. So we'll write down metamers. They are compounds with same molecular formula, same bifunctional group. Bifunctional group. Okay, bifunctional group, I told you which type of group, which attaches this side also alkyl, this side also alkyl. The functional groups which may be present here are ketone, ether, ester, secondary amide or secondary amine. These type of functional groups can show metamerism. Other functional groups cannot show. So a question can be asked like this: which functional group cannot show metamerism? Which functional group cannot show metamerism? Okay, this could be one of the question. So the answer is going to be what? Alcohols cannot show, amines cannot show, then aldehydes cannot show, carboxylic acid cannot show because they do not attach in the middle. Okay, so these are the ones which cannot show metamerism. These can show a functional group which has some alkyls on this side, some alkyls on the other side. Okay, same molecular formula, same bifunctional group, different alkyl group arrangements on both sides. Different alkyl group arrangement on both sides. Okay, so alkyl group arrangement should be different on both sides. That is the condition. Let us see few examples of this and then we will move forward. Let us see few examples of this. Then we are going to move forward. For example, when I take a ketone, pentane 2-on versus pentane 3-on. Okay, pentane 2-on or let's not take pentane 2-on, pentane 3-on. Okay, you can take that. Pentane 2-on is going to look like this. This is pentane 2-on, everybody. This is pentane 3-on. Okay. So I know most of you will confuse it with positional isomerism as well. Because in the positional isomerism, we have seen the functional group will have a different position. Here also, pentane 2-on, ketone is at second number. And here pentane 3-on, ketone is at third number. Now what should we answer? Are they position or are they metamers? So the correct answer is both. Okay, metamers sometimes can be positional isomers as well. They are positional also. So if the question is choose a single option correct, then if both of the options are there like position, meta, chain or both position and meta, answer will be both. It is positional isomerism as well, it is metamerism as well. But if it is single option correct and you can't choose both, then choose metamerism. Okay, so what is the condition here? I told you metamerism will overlap with position sometime. Metamerism sometime will overlap with chain also. But whenever they are overlapping, the more preferred answer will be metamerism. And if both the options are there and you have that answer to choose both, then both are correct. Okay, so we'll mention this point. These two are metamers as well as position isomers. These two are metamers as well as position isomers, but metamerism more preferred over position. But metamerism more preferred. Okay, it's just a rule of IUPAC which says that whenever there are two isomers which are meta as well, position also, you consider them as metamers. Consider them as metamers. I hope this is clear to everyone. They can be called position, yes. They can be called metamer, yes. Why? Because the ratio of alkyl carbons are different. Here the alkyls were in ratio 1:3. 1:3. Here the carbons are in ratio 2:2. So I have changed the alkyl arrangement on the both sides. From 1:3 I have gone to 2:2. Okay, this is how you can talk about metamers. So they are metamers because the number of carbons in the alkyls are different on both sides. And they are position because while naming them, I can see the position of ketone is different. Let me see one more example. Sometimes they can overlap with chain isomerism as well. Sometimes they can overlap with chain isomerism as well. For example, let me take one more example. Example number 2. Let me take a ether of 4 carbon. Ether of 4 carbon. Okay. I can take ethoxyethane, CH3, CH2O, CH2, CH3. I can take this ether where I have kept 2 carbon that side, 2 carbon this side. Its name is ethoxyethane. Other thing what I can do is I can take them in the ratio 3:1. 3:1. 3 carbon this side, 1 carbon that side. Methoxypropane. 3:1, which is methoxypropane. Are they metamer? Yes, obviously. Here the ratio was 2:2. Here the ratio was 2:2. And here the ratio became 3:1. So they are metamers. But by looking at the name, in this the parent chain is of 2 carbon, eth. Here the parent chain is of 3 carbon, prop. So are they not chain isomerism? They are to chain also. So they are chain as well as metamer, but which is more preferred? Metamerism. I hope it is clear to everybody. Can you quickly answer me? Is it clear? Then we move forward. These two are metamers as well as chain isomers. As well as chain isomers, but metamerism more preferred. Good morning, Neeraj, Niranjan. Just type a message on that in the YouTube. You type a message that please click on live or please attend the live class, like this. Please attend the class live. Maybe some of them are please attend the class in live mode. Send it. Maybe they'll see. Okay. Some of you might be watching the class from the beginning part. So that's why I'm not getting any replies. So kindly come to the live mode and watch the class. Okay. Metamerism is more preferred over the chain and position both. Okay, so metamerism is a confusing isomerism. It sometimes confuses you with position, it sometimes confuses you with chain, but it will always confuse you with these two. So you have to remember that more preferred is going to be metamerism over the other two isomers. Okay, is it clear to everybody, yes or no? Is this point clear to everyone? This is about metamerism. Okay, this is about metamerism. Yes, sir. Okay. Can you tell me what is the relation between these two? Or you do the match the following. Be careful and do, everybody. First one is you do the match the following, everybody. Do the match the following. You can match, one. You can match one of the option with many. It's possible for you. Okay, you can do that. Means you can say all are position, position, position. You can say like that. So tell me the answer in the chat box. What type of isomers are these? What types of isomers are these? And what types of isomers are these? A, B, C. You have to tell me whether A represents position, functional, or meta. B represents positional, functional, or meta. And what does C represent? Can you tell me the answer, everybody? A is functional. Okay, Neeraj. C position, B metamer, A functional. And that is correct. Good. A, beta, this is a primary amine and this is a secondary amine. Primary and secondary means directly functional isomerism. Metamerism it cannot show. Metamerism requires to have same functional group. Okay, same functional group. These are the different functional groups. So they cannot be metamer, they have to be functional isomer. Second one, if we look at second one, does it have same number of carbons? Yes, 1 carbon and 6 carbon this side. In the middle there is a ester. So bifunctional group is there. Yes, it is there. Okay, bifunctional group is there. Yes, it is there. Previously, after oxygen, 1 carbon was there. Now, after oxygen, 6 carbons are there. Before carbon, 6 carbons were there. Now, before carbon, 1 carbon is there. So, yes, it has changed from 6:1 to 1:6. So, this is a metamer. Their names are also going to be different. This is benzoate. This is methyl benzoate. Okay, what is this? This is methyl benzoate. Methyl attached to a benzoate. Now, this is ethanoate. Ethanoate. This is a phenyl ethanoate. Okay, what is this? This is phenyl ethanoate. So, yes, they are different compounds. They have same bifunctional group, but the alkyl chain arrangement has become different on both sides. Whereas this is a butene-ol, but different positions are there. If I want to name this one, OH should get the lowest number, 1, 2, 3, 4. It's a but 3-ene 2-ol. Here it is 2-ene 1-ol. But 2-ene 1-ol. So yes, positions are different. So this is going to be an example of position isomerism. So this is the one. I hope it is clear to everyone. I have no idea about Bharti Airtel scholarship, Dimitri Mendeleev. You have to ask Google for that. Okay, I have only knowledge about chemistry. I can tell you things about chemistry, nothing about how the exam is going to be, when is this exam, that exam, nothing. About NEET, if you want to ask something specifically from chemistry point of view, you ask me. So this is the thing. Is this question clear to everyone? Now let us move on to the geometrical isomerism. GI, geometrical isomerism. We saw in the last class that this was the classification. We have already discussed about chain isomerism. We have already discussed about position, ring chain, functional, meta. These we have discussed. Tautomerism will be done at the end. A separate class is required for the tautomerism. When we come to stereoisomerism, stereoisomers are those which have same molecular formula, same structure, but different spatial arrangement. Out of different spatial arrangement, there are two possible options: configurational and conformational. Configurational and conformational. Okay, what is configurational versus what is conformational? See, when spatial arrangement is different and you can keep changing the spatial arrangement, that is called as conformation. Conformational isomerism is not a true isomerism. Okay, they are interconvertible. They keep converting into each other, and conformational isomers are always going to be infinite number of isomers. We don't have to study about conformational isomerism as of now. Okay, in the alkane chapter you will study it anyways. So conformational isomerism is when the spatial arrangement of groups are different and they keep interconverting into each other because of free rotation through a carbon-carbon single bond. Like if I take ethane, if I say, does ethane show isomerism? Answer is no, ethane does not show isomerism. If I look at ethane, does it show isomerism? You will say no, ethane cannot have chain isomerism, ethane cannot have, functional isomerism or any type. But it will have one isomerism of the type conformational isomerism. Ethane can have an eclipse form, ethane can have a staggered form, which is not a true form of isomerism, but still we can talk about it. Okay, it's not a true form of isomerism. This is something you should know. What is configurational isomerism? Configurational isomerism means the configuration is fixed in space. Okay, the spatial arrangement of the groups are fixed. You can't rotate them and change that configuration. Like cis and trans is an example. When you take cis butene and when you take trans butene, this is how cis butene will look like. This is how trans butene will look like. In a cis butene, the two methyl groups will be present on same side. In trans butene, the two methyl groups will be present on opposite side. It's not possible to physically convert cis to trans. It's a fixed configuration. That's why they are an example of configurational isomers. Configurational isomers. So what is configurational? When the spatial arrangement in the space is fixed. You can't change it. Okay. So we'll talk about this configurational isomerism today. It is of two types. It is going to be optical and geometrical. Today we are going to talk about geometrical. Today we are going to talk about geometrical. Maybe after two classes we'll talk about optical as well. Okay. So what is geometrical isomerism? I have written the things on the board. I'll read it from there because I told you the problem with my shoulder for today. And I'll keep explaining wherever required. So what is geometrical, what is configurational isomers? Stereoisomerism, which are not interconvertible. I already told you this point before, beta. So all of you can just write it down in one line, all of you. Configurational isomers, stereoisomers which are not interconvertible. Stereoisomers which are not interconvertible, at room temperature are known as configurational isomers. Means they have a fixed configuration in space. Out of them, who are geometrical isomers? So when you say fixed configuration in space, that fixed configuration may be due to a restricted bond rotation. You remember the word, restricted bond rotation. So whenever the configuration in space is fixed due to restricted bond rotation, we call them as geometrical isomers. Okay, remember this word, due to restricted rotation of atoms around a double bond or a ring. Okay, so restriction comes in a double bond, restriction comes in a ring. Then the geometrical isomerism arises. Okay, so what is GI? Please remember the definition now. What are geometrical isomers? Stereoisomers in which the fixed configuration arises due to restriction in the bond rotation. How the restriction is there, I will show you with the diagram. So it is a type of configurational isomerism which arises due to restricted rotation around a double bond or a cyclic ring. For example, if you look at this structure, okay, it should be movable one, but it's not moving, it's fine, not a problem. Okay, in the PPT it was moving. I'll just show you with the PPT as well. Okay, I had the PPT in which it was moving. Since it is not moving right now, it's fine. I'll just show you. This is how alkene looks like, beta. This is a alkene. Okay, so there is a double bond present here. In a single bond, if I have a alkane, carbon-carbon single bond is cylindrical like this. Okay, let's say I have a carbon-carbon single bond. It is cylindrical nature like this. So you are allowed to keep one atom fixed and you can rotate the other like this. Okay, so till the time I have one finger which is holding on to each other, I am allowed to rotate it like this. Okay, but when I get a double bond, now you see, now I am not allowed to rotate it. If I rotate it, the bond will break. If I rotate this hand, the bond will break. So when there is a single bond, bond rotation is allowed, because single bond has a cylindrical nature. So bond rotation is allowed. It will give rise to conformational isomerism. Okay, there is no restriction in the bond rotation. So at room temperature, ethane will keep rotating from staggered to eclipse, eclipse to staggered. But when we talk about alkenes, in alkene there is a double bond. Double bond does not have a cylindrical nature. In the double bond, actually, pi bond, as you see here, has a cloud-like nature. Cloud-like nature means pi bond will be present above the plane also, below the plane also. So there is like a glue, pi bond attaches on the top of the molecular plane as well as at the bottom of the molecular plane, something like this. So when you try to rotate, it's impossible to rotate. There is a rotation restriction. If I want to rotate, I have to break the pi bond, then only rotation will start. So when there are two bonds, rotation is restricted. Okay. So if the it is cis, let's say cis is like this. This methyl is on the top side. This methyl is on the top side. There is no possibility to make it trans like this, because I can't rotate it. This rotation is not allowed, because otherwise this bond has to break. Once this bond breaks, then only it can rotate. So a cis is a fixed configuration. Same way, a trans is a fixed configuration. Let's say one methyl is here on the top, one methyl is here at the bottom. This is trans. Trans cannot convert to cis by just rotation, because rotation is not allowed. There is a double bond. There is a restricted rotation here. Okay, so that is why alkenes can show geometrical isomerism, and cycloalkanes also can show geometrical isomerism. As the time comes, I will tell you. Okay. So this is cis-butene. Okay, this is cis-butene. You can all see here. Where this CH3 group is on the top side. Here also the CH3 group is on the top side. So when the two are on the same side, we call it cis-isomerism. You can't convert it to trans directly. By some chemical reaction, you can do that. But physically, you cannot do it. You can't just rotate it, because rotation is restricted here. This rotation is not allowed. This rotation is not allowed. And this is trans, where the top CH3 on the left side carbon, whereas the CH3 on the right side carbon is the bottom side. So this is trans but 2-ene. Okay, all right. So what are the conditions to show the geometrical isomerism we are going to study? When is geometrical isomerism possible? So what is a stereocenter? Whenever you need stereoisomerism, either you need GI or you need optical, you need something called as a stereocenter. Stereocenter. The name itself tells you. A center responsible for stereoisomerism. This center can be of two types. You can call it a stereogenic double bond or chiral carbon. There are two types of stereocenters. So when you want to generate geometrical isomerism, you need a stereogenic double bond. What is a stereogenic double bond? A carbon double bond carbon or a carbon double bond nitrogen. Many things can be there. A carbon double bond carbon which satisfies some conditions. A carbon double bond carbon which satisfies some condition. The condition is simple. Carbon double bond carbon is present, then on both the side, the two groups which are present must be different groups. A should not be equal to B on this side. Same way here, alpha should not be equal to beta. This side some AB should be there. That side also AB can be there. That side also AB can be there. These two must be different. These two must be different. If all four are different, also not a problem. On each sp2 carbon, on each sp2 carbon, on each sp2 carbon, if both the groups are different, here also both different, here also both different, then this becomes a stereo center. This whole thing is a stereo center. It becomes a stereo center. Then GI will start occurring. If these two groups become same, no GI, no stereo center. Okay, so to produce GI, you need stereogenic double bond. So it's a geometrical isomerism producer. Whereas a chiral carbon is a carbon having 4 different groups, a sp3 carbon carrying 4 different groups. That is also called as a stereo center. Okay, to produce optical isomerism. To produce optical isomerism, this is one of the conditions to have a chiral carbon. So all of us know what is a chiral carbon. A carbon which is sp3 carbon, and it needs to carry 4 different groups. Let me call it as alpha group, beta group, gamma group, delta group. All 4 groups different. Then this carbon also becomes a stereo center. This carbon also becomes a stereo center. Okay. So what is a stereo center? A stereo center is a center responsible for stereoisomerism. If stereoisomerism is of type GI, you can have a double bond or a ring also. Stereogenic double bond or a ring also might be present. Double bonds are more important in alkenes chapter. And if you want optical isomerism, a chiral carbon can act as a stereo center. Okay. So what is a stereo center? It is defined as atom or bond bearing groups in such a nature that it will produce different stereoisomers. Okay. This is the thing about stereo center. For GI, we want stereo centers with a carbon double bond carbon. Now my question is, you tell me whether the orange one is a stereo center or the green one is a stereo center, or both of them are stereo center. You tell me. Is the orange stereo center or is the green stereo center? In the second one, you tell me, is the orange stereo center or is the green stereo center or is the red stereo center? Who is acting like a stereo center? Just find the stereo center for me. In the first example, is orange stereo center? Is green stereo center? In the next one, is orange stereo center? Is green stereo center? Is red stereo center? So that is the question. First one, orange is the stereo center and green is not? Yes, green is not stereo center, but orange is stereo center. Very good. So in the first one, orange is a stereo center, green is not a stereo center, because here both the groups are same on the carbon, CH2. If 2 hydrogens are there, this cannot show GI. So this part cannot show GI, but this carbon double bond carbon can show GI, can show geometrical isomerism. So cis trans can exist here. If both the hydrogens are same side, it is cis, opposite side trans. This one cannot show GI. So I can draw the 2 isomers as well now. 2 isomers will be possible, everybody. I can draw a cis. Cis will look like this. Please see here, everybody. CH3. On this carbon, hydrogen is downside. On the other carbon also, I am keeping hydrogen on downside. So CH double bond CH2 on the top side. This is cis isomer. This is cis isomer. Now I can draw the trans isomer of this as well if hydrogens are on opposite side. So CH3 carbon, this hydrogen is downside, whereas this hydrogen is upside. And here CH double bond CH2. So cis trans arises because of the orange double bond and not because of the green double bond. So this is trans isomer. Okay. Yes. In the second one, red as well as green, some are saying that is correct. Red as well as green. Very good. Very good. Orange is not because the two hydrogens are present here. So this sp2 carbon is not satisfying the condition. So this cannot become a stereocenter. If I look at a green one, in the green one there is a H present and there is a vinyl present. Yes, different. On this side there is a H present and there is another vinyl type of group present. So yes, this has two different groups on this side and two different groups on that side. So it will show. And will the red show? Yes, red will also show. Red has a methyl this side and a hydrogen. On this carbon, it has a hydrogen and a big group. So both the groups are different on both sides. Red will also show isomerism. So how many different isomers will be possible here? Okay, how many different types of isomers will be possible here? So simple formulas will come at the end of the class, which is 2 to the power n, where n represents stereocenter. Okay, so if you have two stereocenter, 2 to the power 2, 4 isomers will be possible. 4 isomers will be possible. When there is one stereocenter, single stereocenter, 2 to the power 1, 2 stereoisomers. One is cis, one is trans. So this one, stereocenters are 1 in the first one. Stereocenter. Let me call stereocenter as n. If n value is 1, then total geometrical isomers are 2 to the power n, which is 2 isomers. 2 isomers. Keep remembering these formulas. Okay. This is only valid, this formula is only valid when you have an asymmetrical molecule. When you have a asymmetrical molecule. Okay, asymmetrical molecule means which type of molecule? A molecule which does not look identical from both sides. Okay, molecule which does not look identical from both sides. This and this does not look the same. No, this side there is a methyl, this side there is no methyl. So this is an asymmetrical molecule. This is also asymmetrical molecule. This corner is a methyl, this corner is something else. So for an asymmetrical molecule, total geometrical isomers are always 2 to the power n, where n is the stereocenter. And here it's an asymmetrical molecule. So stereocenters are 2, n is equal to 2. You can see here, n is equal to 2. So total GI will be 2 to the power n, which is 2 ki power 2, which is going to be 4. 4 isomers will be possible. 4 GIs are possible for this compound. Okay, what are those 4 GI? You can see here. The green one can be cis, red can also be cis. So cis, 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 trans, trans, cis, trans, trans. 4 options are possible. Again, I am telling. Green can be cis trans, red can be cis trans. Okay, so total 4 options are there. If green is cis, red is also cis, cis, cis. Green is, or I'll just show you with the numbering. Okay, you can see here, it's IUPAC numbering will start from this side, all of you know, because alkene should get the lowest number. 1, 2, 3, 4, 5, 6, 7. Okay, so it's a heptatriene. What is this? It's a heptatriene. Third alkene shows GI and fifth alkene shows GI. Third will have a configuration and fifth will have a configuration. Third will have a configuration, fifth will have a configuration. Third will have a configuration, fifth will have a configuration. Third will have a configuration, fifth will have a configuration. So one type of heptatriene possible is 3 cis, 5 cis heptatriene. 3 cis, 5 cis heptatriene. Second will be 3 to cis, but 5 become trans. 3 cis, 5 trans. Then next could be 3 trans, 5 cis, or both are trans. 3 trans, 5 trans. So is the formula clear to everyone? 2 to the power n. Please use this formula only when the molecule is a symmetrical molecule. Is the formula clear to everyone? I am just waiting for a reply and then we'll move ahead. Whenever a molecule is asymmetrical, their stereocenters are n, 2 to the power n GIs are possible. Okay. All right. So the conditions are, I just told you, these conditions I already have told you. There should be a restricted rotation, which means there should be a carbon double bond carbon, and there is different functional group system which can show like double bond is there. And ring also has a restricted rotation, as you can all see here. So if this is a carbon, this is a carbon, they are attached by a single bond, but there is another CH2 group in between. Now this also creates a restricted rotation, like this. This also creates a restricted. If I have a triangle, triangle will look like this. So although the these two carbon are attached by a single bond, but because there is a third carbon in between, I can't rotate it. Only when the bond will break, rotation can start. So a ring also is a center of restricted rotation. Okay. In the ring also same way, you just look at this carbon carry 2 different groups, this carbon carry 2 different groups, then geometrical isomerism will start. If A and A are on same side, it is cis. If A and A are on opposite side, it will become trans. It is possible in a 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring, any ring you take, there is a possibility of isomerism. When the possibility is there, you must remember that ring must be bi-substituted. Ring must have 2 substitutions on different carbons. At least 2 substitutions. At least 2 substitutions on different carbons. Then it will show GI. Very important point. Okay. 2 substitutions should be there. 1 substitution not valid. At least 2 substitutions should be there. So things like this has no substitution. All are hydrogen. So it cannot show GI. This cannot show GI. Yes, this will start showing GI. This has 2 substitutions on different carbon. This will not show GI because I can't see any 2 carbon which carry 2 different groups. Okay, this carbon carry both hydrogen. This carbon carry both hydrogen. This carbon carry both methyl. So it cannot show GI. So which can show, which cannot show? This cannot show GI. This cannot show GI. This can show GI. This cannot show GI. Let me show more example. If I have something like this. Now there are 2 substitutions. So these 2 carbons have a restricted rotation. You can have the hydrogen up, here hydrogen up, cis, or hydrogen up and down trans. So this can show GI. 2 substitutions are required. Okay. 2 substitutions are required. Cl, Cl, CH3. Okay. Can this show GI? Can you tell me? Can this one show GI? Answer will be no, sir. I can't see any two carbons. See, this carbon carry both chlorine. This carbon carry both hydrogen. So they cannot show. This carbon carry a methyl and a hydrogen. Okay. So only there is one carbon who carry two different groups. There are not two carbons. Okay. Two carbons are not present with the different groups. So no GI. It cannot show GI. Cis trans. How will you have cis trans? How will you have cis trans? This cannot show beta. There must be two carbons in a ring. Two carbons minimum. At least two carbons which carry two different groups. H methyl, H chlorine. Yes, possible. In this one, this carbon carries a H and a methyl. This carbon carries a H and a chlorine. Yes, two carbons with different groups will show GI. If 3 are there, it will show. 4 are there, it will show. At least two carbons must be there. In this case, only there is one carbon who is satisfying the condition. There are no two carbons. So how will you have cis trans? A single carbon can't show cis trans. No, at least two carbons must be there. Okay. This carbon has both chlorine. This carbon has both hydrogen. Not applicable. Not applicable. Like this, we will check. Okay. As the class proceeds, I'll show you different examples as well. Okay. This will not show GI because the groups became same here. This will show GI because the groups are different here, and here also groups are different. So the carbon, sp2 carbon, must carry two different groups to show GI. So this will show GI. This will not show GI. Okay. So when we have to name geometrical isomers, there are three ways of naming beta: cis trans, EZ, and syn-NT. Cis trans, EZ, and syn-NT. When to use cis trans? You will use cis trans. You will use cis trans when on a stereogenic double bond, on the two carbon, at least one group is identical. At least one group is identical. Let's say I have a group A here, B here, D here, A here. So what happened here is these two groups became identical. So whenever one of the group on both the carbons is same group, then cis trans will be used. Then you will use cis trans. If they are on opposite side, I'll call it trans. If they are on same side, I'll use cis. Okay. One atom or group must be same on both the carbons of stereocenter. When to use EZ? You will use EZ when all four groups are different. All four groups are different. Something like this. Carbon, double bond carbon. Here we have A. Here we have B. Here we have X. Here we have Y. Now obviously cis trans will not work. There is no same group. So I can't say A is opposite to A. So in this case, cis trans is not applicable. We'll use EZ. It will be E or Z. Okay. So cis trans will be used when one group is same. If all four groups are different, we'll use EZ. If all four groups are different, we'll use EZ. When to use syn-NT? Syn-NT is used in some cases of di-azo compounds. Okay, you can call it azo compounds. When groups are not present, but lone pairs are present. One example I am just mentioning here, like N double bond N, this type of compounds when you have, if the two lone pairs are on same side, you will be using syn naming. When the two lone pairs come on opposite side, you will be using NT naming. Not very important for the NEET, but syn-NT is also one type of geometrical isomerism which actually can exist. So restricted rotation does not mean only carbon double bond carbon. It may be nitrogen double bond nitrogen also. So in the case of azo compounds, you will use syn-NT. Another case will come, which is case of oxymes, where again syn-NT can be used. Not very important for the NEET. Cis trans and EZ are the two important cases. Okay. So now a question to you. You can tell me, so I've told you what is cis trans already. Okay. In cycloalkane also I've told you all this part. My question is, this is your NEET type of question. NEET 2025 also has asked this type of question, same type. You need to tell me which of the following compounds will show GI. 1, 2, 3, 4, 5, 6, 7, 8. 8 are written here. Which will show geometrical isomerism is the question. I'll give you 5 minutes to solve it. Draw all their structure and then tell me the answer. Who will show GI? Who will not show GI? Before moving ahead, you can like the video if you are enjoying the classes. Okay. If you remember, same type of question has come in NEET 25 as well. Ethene, will it show? Answer is no, sir. There is no stereocenter here. Both the carbon are carrying. Yes, Mohit. Propene. Propene will show. No, sir. Propene will also not show because this carbon carry both the hydrogens only. So there is no possibility here. There is no possibility here. 2-methyl-butene. No, sir. This carbon carries both the methyls only. So this will also not show GI. This will also not show GI. This will also not show GI. Butene, yes, it will show. This carbon carries two different groups. This carbon carries two different groups. So this becomes a stereocenter. So answer is yes, it will show. Penta-1,3-diene. Penta-1,3-diene. This is penta-1,3-diene. So this side, though we cannot have isomerism, but this carbon double bond carbon can act like a stereocenter. So yes, this will also show geometrical isomerism. 1,2-di-deuterioethene. Deuterio means deuterium is attached. So yes, it will also show. This is ethene. But now I have kept one deuterium here, one deuterium here. So now these are two different atoms. Both are different atoms. Hydrogen is different, deuterium is different. So yes, this will also start showing you stereoisomerism now. GI it will show. This is showing, this is showing, this is showing. Phenylethene. Answer is no, sir, because here both are hydrogens. So it will not show. Buta-1,3-diene will also not show. If you draw buta-1,3-diene, this is buta-1,3-diene. So in this carbon, both are hydrogen. It will not show. On this carbon also both are hydrogen, it will not show. So answer is 4, 5, 6. Answer is going to be 4, 5, 6. Now, a few different properties we should remember for cis versus trans. If we do a comparison of a symmetrical cis like a butene cis and butene trans, if we do their comparison, we should know few properties about them, that who has better boiling point, who has better melting point. Sir, please fifth again. Penta 1,3-diene beta, draw penta 1,3-diene. This is penta 1,3-diene, 1, 2, 3, 4, 5. Penta 1,3-diene. This double bond cannot become a stereocenter because on this side carbon has two same groups. Carbon has two same groups. But this one, this alkene has hydrogen and a methyl, different groups. This one also has a hydrogen and a vinyl, two different groups. So from here it can show cis trans. Okay. Someone is asking why not 8? Beta butadiene, this is butadiene, buta 1,3-diene. On this side carbon has two hydrogens. So this alkene is not satisfying the condition. This side also, this sp2 carbon has two hydrogens. So this alkene is also not satisfying the condition. Okay. So let's see some of the properties. Properties like, first we'll see stability. Then we'll see heat of hydrogenation. Heat of hydrogenation, stability, heat of hydrogenation. Then we are going to see polarity. With polarity, we can also talk about volatility. With polarity, we can also talk about boiling point. We can also talk about vapor pressure. We can talk about melting point. Okay, these are the things which we can talk about the orders. Okay, these are things where we can tell whether cis is better or trans is better among these properties. Okay. When it comes to stability beta, stability depends on repulsions, and you can see that cis is going to have more repulsions. So cis is going to be unstable. But trans, because the two bulkier groups are opposite side, trans will be stable. Less repulsion, more stable. So stability wise, trans is better than cis. Stability wise, who is better beta? Trans is better than cis. Okay. When we talk about heat of hydrogenation, heat of hydrogenation is inversely proportional to stability. Please remember this. Heat of hydrogenation is inversely proportional to stability. I am writing it as delta H hydrogenation, means enthalpy of hydrogenation, magnitude, is inversely proportional to stability. Now, how can we imagine it? It is easy to imagine. It is very, very easy to imagine. Let's say this is the energy level diagram I am making. This is energy. We know that potential energy is inversely proportional to stability. So cis butene is unstable, means it is more energetic. Trans butene is stable, means it is less energetic. Cis is here, trans is here. Okay, heat of hydrogenation means how much heat is released when I add hydrogen into alkene. So when you add hydrogen into it, you know that both of them are going to become butane. Let's say butane has this level. This is where butane is. This is the final product, butane. Butane. So product of hydrogenation of cis-butene is also butane. Product of hydrogenation of trans-butene is also going to be butane only. Something like this. Okay. And delta H means the difference between energy of reactant and product. So this is the energy of cis. This is the energy of trans. And this is the energy of product. So what is delta H? Delta H is the difference between energy. So this is going to be delta H for cis. This is going to be the delta H for trans. So trans will release less heat on hydrogenation and cis will release more heat on hydrogenation. Okay. Please remember, very, very important point. So delta H is more for cis, less for trans. More the stability, less amount of heat released on hydrogenation. Okay. So this is the way to check. So we can mention easily that in heat of hydrogenation, cis is the winner. Wherever cis will be the winner, I'll write with the black pen. Okay. Or let's write with the brown pen. Cis is better than trans. Polarity. Beta, polarity, all of you know, depends on the dipole moment. Dipole moment is a vector. So whenever the vectors are adding up together, dipole moment will be high. Whenever vectors are cancelling out each other, dipole moment will be low. So in the trans, you can all see the dipole moment is going to add up. sp2 carbon is more electronegative, so there is a dipole moment going in this direction. Here a dipole moment is going in the upper direction. Both will cancel out each other. Trans will become non-polar. Trans will become non-polar. Every trans alkene is not non-polar, beta. Only symmetrical trans alkenes are non-polar. Symmetrical. If it is asymmetrical, let's say here no hydrogen but chlorine is present, then it will not be non-polar. So symmetrical trans alkenes are non-polar. Cis will be polar only because both the dipole moments are going in same direction. Down, down. Both will add up. So this will be polar. So cis has more polarity than trans. So in this case also, cis is the winner. In this case also, cis is better than trans. The one which is more polar has more dipole-dipole interaction. More dipole-dipole interaction, more boiling point. So in the boiling point case also, cis will be better than trans. Cis will be better than trans. Okay, all of you know about this. Now, whenever boiling point is more, volatility is less. So cis is more boiling point, means cis is difficult to evaporate. Cis has less volatility. So trans is better in volatility. Trans is better than cis in volatility. For example, when you take water versus acetone, okay, acetone or ether, let's take water versus ether. Ether is generally used in the nail paint remover. So when you take a drop of nail paint remover, suddenly it will evaporate. Highly volatile. Okay. Whereas water, which has very high boiling point of 100 degrees Celsius, water takes a lot of time. You can take an example of sanitizer versus water. So when you wash your hands do not dry easily. Water has high boiling point, very low volatility, does not evaporate. But when you take hand sanitizer, sanitizer is majorly propyl alcohol. Alcohol has lower boiling point, means higher volatility. So this is the one. Vapor pressure is also directly proportional to volatility only. More volatile, more pressure will be generated by the vapors. More volatility means more vapors will generate, more vapor pressure will generate. Okay. In the melting point case, please remember trans is better than cis. In melting point case, trans is better than cis. See, melting occurs for solids. Melting occurs for solids. So for the melting point, you don't have to look at the polarity. For the melting point, you need to look at packing. Okay, melting depends on packing. Melting point is directly proportional to packing efficiency. Means which molecule can be better packed. And packing में trans is better. Trans has better packing. Okay, you can think of it like whenever you go and purchase shoes from the market, how the shoes are put in the box. Tell me, whether shoes are put in the box in this manner or shoes are put in the box in this manner. Which way the shoes are put in the box? Tell me. This way the shoes are put or the second way? First way or second way? When you purchase shoes from the market, do you find that in the box shoes are put in the first type way or the second type? Second one. Good, Sharanya. Second one. So second is trans only, na beta. The two heavier side of the shoe, which is your toe side. Toe side is bigger in the shoe. Shopkeeper will always keep it in the opposite way, just so that he has to use a smaller box. Here a smaller box is required, so better packing. Okay, we don't want to waste the space. So by taking trans way, packing will be better, and in a small box also shoes can fit. If I go by first way, I have to take a bigger box, which is cis way. So cis is not good to pack. Trans is always good to pack. These are all the things about the cis and trans isomerism, and we'll keep it till here. In the next class, we'll see how to check EZ with few examples. If it is clear to everyone, please mention a clear in the chat box, and you can like the video and study for the day. Okay. Thank you. Bye-bye. Thank you. See you all in the next class. Bye-bye.